All right, so in the second part of this lesson, we're going to go over inflection points. So inflection points are essentially points on the graph of a function where the graph changes its concavity. So it can change from concave up to concave down, or concave down to concave up. So remember, like a U, an upside down U, or upside down U to U. And I'm going to show you in a minute an example of what these can look like on the graph. And so if we know there's an inflection point, let's say at C comma f of C, then that means that we take the second derivative at that value, we take f double prime of C, then it's either going to be equal to 0 or it's going to be undefined or it's not going to exist. So we're going to use this to help us find inflection points. Now be careful, and I'm going to mention this multiple times throughout these lessons. Be careful to make sure that you recognize that it doesn't mean that the converse of this theorem is true. In other words, it doesn't mean that if the second derivative is 0, or you find that it doesn't exist, it doesn't mean that then there's going to be an inflection point. So again, if you find that the second derivative is 0 or it doesn't exist somewhere, that doesn't mean necessarily there's going to be an inflection point. Remember, it's just saying that if you know a point is an inflection point, then the second derivative there is going to be 0 or it's not going to exist. But let's first go over like a geometrical depiction of what this looks like so you can understand a lot better. So going back to the first graph in this lesson, remember that we have a graph that can go concave down, concave up, and then switch. So like first, the graph is going concave down. It's going concave down here up to here, and then it's going concave down here on this part. And it's also concave down here. All the three parts I have in blue or whatever that color is. Concave up, as you know, I have it in purple. This part, this part, this part. The inflection points occur where the concavity changes from upward to downward or downward to upward. So an inflection point would be right here. B at B, B F of B. So here's one inflection point. Another one would be over here at C F of C. And then another one would be over here. Third one would be here. Notice I didn't pick this one because here it's concave up on both ends. So this is not going to be an inflection point. Also, here it does change from concave down to concave up, but this is not going to be an inflection point because it's not a smooth, continuous graph. The derivative there is not defined because the derivative from the left is not the same as the derivative from the right. Most textbooks, address this. There are some textbooks that actually still counts as an inflection points, so be careful about that. But for the most part, this will not count as an inflection point because, again, it's not a smooth curve. You got like a kink there, and so it's not differentiable there. Let's go through practice problem now. Let's go through 19 and let's discuss the concavity of this graph here. So we want to figure out where the inflection points are, and then let's describe what the graph looks like in terms of its concavity. So let's first find the second derivative, then determine where the second derivative is 0 or undefined, and then study the intervals around that point. So first, let's take the second derivative. First derivative, our rule will be 4x cubed minus 12x squared. Taking the derivative again, we'll get the second derivative be 12x squared minus 24x. We set this equal to 0. solve for the zeros of this. And so the zeros, let's factor that. 0 will be 12x, and x minus 2. So we're going to check the x values. X equals 0 and x equals 2. Because 0 times 12, that'll make a 0 there. And the other 0 will be a 2. So we need to check what's going on around these points. So we're going to break our interval up at these points, kind of like how we were going about studying the graph and figuring out where it's increasing or decreasing. So I like to set up a table just like usual, just adding, the concavity to it. So let's have the first row be the interval. Then the second row will be a test point in the interval. So we look at the sign of the second derivative in those intervals. Let's look at the graph function. So interval broken up at 0 and 2. So we're going to go from negative infinity to 0. And we're all good here because we don't have any undefined values for the function, so we just have to break it up at these 2 points. So going from negative infinity to 0, then we go from 0 to 2, and then 2 to infinity. We want to see what's going on in these 3 intervals and pick a number that's easy to work with. So I'm going to pick, x equals -1, x equals 1, x equals 3 here. And evaluate the second derivative for these 3 x values. So I want to see what f double prime of -1 is. F double prime of 1. F double prime of 3. Plug -1 into the second derivative equation here. The 12 times -1 squared minus 24 times -1. That'll give me just 12 times 1, or just 12 plus 24. So I'll get 36. 36 is a positive number. So positive, I'll put a plus sign. That's good. We really just care about the sign of the second derivative. Double prime of 1 now. 12 times 1 squared minus 24 times 1. 12 times minus 24, you'll get -12. You have a negative number here. Negative. That value. And then f double prime of 3. 12 times 3 squared minus 24 times 3. 12 times 9, it will be 12, 90, 108 minus 72. That should be 28, 36. It's still positive. Positive 30. And so our graph is going to be concave up here. So I like doing this. Concave up. Here it's going to be concave down. Second derivative is negative. And here it'll be concave up. Now, when you first start working on these, I recommend drawing a sketch of it. I usually make my students draw a sketch so they can connect the concept and not just get lost in the calculations. So let's draw a sketch of what this function would look like. So I'm going to essentially find what f of 0, and f of 2 are. That's kind of like the main thing. So let me actually, let's do this. These are where the inflection points are. Inflection points. And kind of ask, like, when you first start, like, are there inflection points here? And if you look at x equals 0 and x equals 2, you want to see what's going on before and between them. So see, before x equals 0, it's concave up. Then after 0, it's concave down. So there's an inflection point here. So there's an inflection point at 0, f of 0. We got one there. Then we look at what's going on around x equals 2. Before it's negative, after 2, it's positive, concave up. So there's also an inflection point at 2, f of 2. See, if it was like both concave up here, this wouldn't be an inflection point. You know, it's not changing concavity. But since it changes concavity at these 2 points, these will qualify as inflection points. So there are 2 inflection points. Like I say, it's concave up here, concave down, concave up. Now, I'll save you the trouble for calculating these. I already, did them, but at f of 0, kind of do it in your head. F of 0 is just gonna be 0 because you plug in 0, you get 0. So I like that 0, 0. At 2 comma f of 2 is going to be, 2 to the 4th, 16 minus 4 times 2 cubed, so minus 32. So then f of 2 is actually negative 16. Just a sketch. So 2 negative 16. And so what's going on here is that before 0, 0, it's concave up. So it's doing something like this. And from 0 to 2, it's concave down. It's doing this. And afterwards, it's concave up. Graph of f looks like this. And the minimum, if you were to calculate it, would occur at 3 comma negative 27. And y-intercept would be at 42. Just to save you time, I won't go through all the work because the main focus is to understand concavity.